For this next lesson, we are going to look at how signed area can be used to help us find actual areas and evaluate some slightly more challenging integrals and how we can look at that. Okay, so let's look at an example. And in this one, we're just going to take a little bit, we're going to find a definite integral, but we're going to take a little bit of a closer look at what that means about the graph. Okay, so I want to find the integral from 0 to 2 of x squared minus 1 dx. Okay, and what we're going to do is we're going to look here at minus 1, and we cross the graph here at 1, and then we have a point at 2, comma 3. So that's what this graph looks like. Okay, so what we notice is we have some area that is underneath in our interval, some area that's underneath the x-axis, and we have some area that is above the x-axis. So how is our integral going to treat each of these different kinds of area? So let's, in order to see how it treats it, let's first just take the integral. Okay, so we're going to find the indefinite integral, which is x cubed over 3 minus x. We're going to evaluate that from 0 to 2. So this is 2 cubed over 3 minus 2 minus 0 cubed over 3 minus 0. This last part is certainly just 0. So we get 8/3 minus 6/3, which is 2/3. Okay, so this is right here what we call the net signed area. Okay, so this is going to be, it's not going to be the total shaded area we have here. We're treating the yellow part of the area and the green part of the area differently. So let's see how it actually breaks down. So let's say instead of just finding the integral, I asked a different question. So let's say I have the same graph. Okay, this is 2. So this is f of x equals x squared minus 1. And I want to ask the question, I want to find, instead of doing that, I want to instead of just finding the net signed area, I want to find the shaded area. Okay, so remember, our integral is going to treat any area that's below the x-axis as negative, so this is going to be minus, and any area that's above the x-axis is positive. So it crosses, our x-intercept here is at 1. So what we want to do is we're going to take our integral separately. We want the integral from 0 to 1 of x squared minus 1 dx. And what we're going to do is we're going to take, this would normally be negative, we're going to make it positive because we want to actually just find the area, and the area is positive. The area we get from an integral has a sign. So we have the area, the integral from 1 to 0 of x squared dx. This is the whole area below the x-axis. This is x cubed over 3 minus x evaluated from 1 to 0. So this is 1/3 minus 1 minus, this all comes out 0, which is negative 2/3. So the area under the graph, okay, the area, so the positive area between 0 and 1 is 2/3. Okay, so now we're going to find the area between 1 and 2. So we're going to take the integral from 1 to 2 of x squared minus 1 dx. So we have, again, x cubed over 3 minus x, and this time we're going to be evaluating it from 2 to 1. Okay, so we have 8/3 minus 2 minus 1/3 minus 1. So we are going to be adding 1, subtracting 1/3. That ends up being 7/3 minus 3/3, which gives us 4/3. We're subtracting 1/3. And then we are adding 3. So let's actually work this out. I feel like maybe my notes are a little bit wrong. So 8/3 minus 1/3 is 7/3. Minus 2 plus 1 is -1. So we are going to be subtracting 1 or 3/3, which gives us positive 4/3. Nope, my notes were right. My brain was wrong. Okay. So here, because this is above the axis, this area is, okay, and this is above the axis. So this area is going to be positive. So the area between 1 and 2 is 4/3. So the total area and the total shaded area is 2. So it's 2/3 plus 4/3, which is equal to 2. So this isn't the same as finding the integral. So we've addressed this problem in 2 different ways. The net signed area is 2/3. That actually ends up being the difference between the green area and the yellow area. The total area, when we add them together, means that anything below the x-axis we need to treat as negative, and then we need to negate it. And the total area above the x-axis is positive. So what we need to do, the important thing here was that we knew exactly where this function crossed the x-axis, what its x-intercept was. Okay, so let's now look at another example. Okay, and where else can understanding this signed area help us? Well, we want to evaluate the integral. Okay. Integral from 0 to 4, absolute value of x minus 2 squared minus 1 dx. So what does that look like? Well, when we take the absolute value of a function, so let's think about our function. Okay, so this is a parabola. Its vertex is at 2, -1. So we go over 1, 2, and down 1. That's the vertex of the parabola. It is a standard kind of parabola, so it has an a value of 1. So we can go over 1, up 1, over 1, up 1. Okay, if we were just graphing this, now over 1, up 3. So what we're looking at, the absolute value of the function takes everything that's below the x-axis and flips it upward. So this absolute value parabola has a vertex at 2, +1, but it kind of does this funny flippy thing. So we want to take the integral here. So we're looking at finding this green area right here. Okay, and right here. We're going from 4 to 0. Okay, this is our 4. And we also want to find the area under here. So when we're taking the absolute value, because we're reflecting above the x-axis, what we can see is that this green area is the same as what this yellow area would be below the x-axis. So this would be our negative area down here. And then the green area is just the positive version of it. So what we want is we want the negative. We can just take the integral of the function without the absolute value sign from 0 to 4, but we're going to have to do it in pieces. Here we want it to be positive, just exactly as it is. Here, if we take the integral of the function without the absolute value sign, this part would come out negative. We want it to come out same thing but positive. So this, we're going to have to subtract. So what we would set up here, this is going to be the integral from 0 to 1 f of x minus the integral from 1 to 3 of f of x plus the integral from 3 to 4 of f of x. And now you can use some geometric properties, and we're going to say f of x equals just x minus 2 squared minus 1. So we can now use some geometric properties to help make this a little bit easier. So one of the geometric properties, even though my drawing doesn't quite reflect that as perfectly as I would like it to, one of the geometric properties of parabola is that they are symmetric and that they have, in fact, a line of symmetry. So everything to the left of the parabola, so we have right here, the integral from 3 to 4 should be the same as the integral from 1 to 0. So we are just going to have to do the integral here from 1 to 0, and we're going to just double it. We don't actually need to use that because of the geometric properties here. Okay, so now let's actually take our integral. So 2 times, and we've got x minus 2 squared. Luckily, the inner derivative of x minus 2 is just 1. So this is x minus 2 cubed over 3 minus x, evaluated from 0 to 1, minus x minus 3 cubed over 3 minus x, evaluated from 1 to 3. So notice we're subtracting this here because we know that from 1 to 3, this is actually going to come out negative. Okay, so let's plug everything in. So this is equal to 2 times negative 4 thirds minus a negative 8 thirds minus 1/3 minus 3 minus a negative 4 thirds. So this is equal to 2 times 4 thirds minus just a negative 4 thirds and this gives us 8 minus 12, so this is 12 thirds, which equals 4. Okay, so one last problem. We have example 3 of how we can use this geometric, how we deal with this kind of signed area. So let's take f of x equals cube root of x. Okay, so that looks like this. It actually is not differentiable right there at the origin. We have this here, we have this going down here, a cubic flip reflected over the line y equals x. And let's say we want to find this shaded area here and here. Okay, and so we are being asked again to find the shaded area. Instead of actually finding the signed area. So note, we know that radical cube root of x, y equals cube root of x, is an odd function. Okay, so what it means to be an odd function, because we can reflect, it means that the integrals, so right here, the area here is actually going to be the same on both sides, given that the x values are the same on both sides. So this one is not, because we have -1, -2, -3, and here we're only going 1 and 2. Okay, so how can we set this up? Well, we know that negative, if we negate the integral here, so negative the integral from -3 to 0 of x to the 1/3 dx, because we know that from before 0, this is negative, it's below the x-axis, so we want to negate it to make it positive. We're going to add the integral from 0 to 2, x to the 1/3 dx. Okay, so this is equal to -3/4 x to the 4/3, evaluated from 0 to -3, plus 3x to the 4/3 over 4. So this one is negative, this one is positive, same thing, and this one's evaluated from 0 to 2. And then this is going to be equal to 9 the cube root of 3, because we're subtracting stuff done to a -3. And remember, we're taking the negative here after we've done all of this cube rooting, over 4 plus 3 the third root of 2 over 4. And anything with a 0 is just going to be 0.